Last time we showed that Brownian motion can be characterized as the unique, continuous, centered Gaussian process whose covariance function is S min t. This is very useful for recognizing Brownian motions out in the wild, sometimes in unexpected places. Here is a nice theorem that tells us how to construct new Brownian motions by transforming a fixed Brownian motion from the start. If Bt is a Brownian motion on the positive real line, then the following processes are all also Brownian motions relative to their own filtrations. The negation of Brownian motion, sometimes called reflected Brownian motion, is its own Brownian motion. We'll soon see that reflected Brownian motion can be more general. We can do these reflections at a sequence of random times stitching together. We can also do what's called the diffusion scaling of Brownian motion, rescale time by some positive parameter c, and then rescale space by c to the minus 1/2. Now, you can imagine that this follows also from Donskirch's theorem, where we did exactly this kind of rescaling of random walk to get to Brownian motion in the first place. So you can prove that this is a Brownian motion from Donskirch's theorem by incorporating a extra parameter for scaling in Donster's invariance principle. But we'll also see it following easily from the Gaussian process characterization of Brownian motion. Here is the most controversial and also most useful example in the bunch, time inversion. If you take Brownian motion at 1/t and scale up by t, then this is also a Brownian motion. Note, this isn't even defined at t equals 0, so there we define it to be 0. All of these are standard Brownian motions, which are 0 at 0. And then the last two examples are related to Martingale and Markov characterizations of Brownian motion. If I take some positive time capital T, I let Brownian motion flow until time t, and then look at where it goes after that, except I don't want to start at bt, I want to start at 0, so I subtract off where it got at time t, then this is a new Brownian motion. Not only is it a Brownian motion, but this process is independent from the Brownian motion up to time t. We can also reverse time in this example in a linear way. That is, we can take the Brownian motion starting at the end time and flowing backwards, and again subtract its value at the end point in order to get a new Brownian motion. Although we have to be careful, this only makes sense when t is less than or equal to that capital T. But on that domain, we do get a new Brownian motion. In all of these cases, to show the result holds true, all you have to do is show that the process involved is a continuous, centered Gaussian process with this as its covariance function. And in most of these cases, all of that is basically trivial. For example, this one here is quite obviously continuous. It's just a linear transformation of a Gaussian process, so it's Gaussian. And of course, its covariance is just putting a minus sign in two places, canceling out, giving us the same covariance. So boom, that one's done. And I'm going to leave it to you to do these ones, which are almost as easy. In each case, it's very simple to see that the process is continuous and centered and Gaussian, since they are linear combinations of other Gaussian processes. The only one that takes a little bit of work to really see is example C here, time inversion. So let's work through the details of that one. So Ct is t times b1/t at positive time, and it starts at 0, at time 0. We need to check that this is a Gaussian process. Well, let's take the process at some collection of times. By definition, that's t1 b1/t1, t2 b1/t2, down to tn b1/tn. And I can write that like this. I can take out those t's as a diagonal matrix, multiplying the vector bs1, bs2, down to bsn, where I'm defining sj to be 1/tj, if tj is not 0. If tj is 0, I don't want to define sj to be infinity because I don't know what b infinity is. But it doesn't matter how I define it. I'll just define it to be 0. because in the case where one of these s's turns out to be 0, that means that we're multiplying by tj, which is 0. So we're just getting a 0 there. Well, now, this is a linear transformation of a Gaussian vector. This is Brownian motion at some collection of times. And so it is a Gaussian random vector, which shows that C is a Gaussian process. For the mean and covariance, well, the mean is straightforward. The expected value of Ct is t times the expected value of b1 over t, and that is t times 0. For the covariance, the expected value of Cs times Ct is the expected value of S b1 over S times T b1 over T. I'll pull out the S and the T, and I know how to compute the expected value of the Brownian motion at 2 times. That's just going to be S times T times the minimum of 1 over S and 1 over T. Now I could write that in terms of the reciprocal of the maximum of S and T, but it's probably easier to just, let's say, take S less than or equal to T. In that case, 1 over S is bigger than or equal to 1 over T, in which case this becomes St times 1 over T being the smaller, which gives us S, which is S min T. And by reversing the roles of S and T, we see that we get S min T in both cases. So we do have the right mean and covariance. So we have a centered Gaussian process with the right mean and covariance. In particular, that means that this is a pre-Brownian motion. All we have to do is check continuity. Now, the only place continuity isn't already clear is at time 0, because this is a continuous process and this is a continuous function. So the only issue is what happens as t goes down to 0. Of course, that could be a very bad discontinuity. b1 over t, in principle, could oscillate wildly, exponentially fast if we want there, and things could all go to you-know-where. But actually, we don't need to work hard at all to see that we get continuity at 0. Because, as we just noted, from the finite dimensional distributions, which are determined by the fact that it's a centered Gaussian process of the given covariance, the process Ct is a pre-Brownian motion. And since it's a pre-Brownian motion, by Kolmogorov's continuity criterion, it has a continuous version. But a continuous version of a pre-Brownian motion is Brownian motion. So what we have here is that this process Ct is a version of Brownian motion. And it's a version of Brownian motion which is already known to be continuous everywhere except possibly at time 0. But here's the thing. If I have two processes that are versions of each other, and they're both continuous except at even a countable number of points, then they must be indistinguishable, just because a countable union of measure 0 sets has measure 0. So therefore, C and C tilde are indistinguishable, which means that C is indistinguishable from a Brownian motion. It is Brownian motion, which is what we needed to show. That time inversion symmetry is super handy because it allows us to deduce large time behavior of Brownian motion from small time behavior. And to see one example of that, let's now look at a version of the law of large numbers for Brownian motion. If we have a standard Brownian motion and we have some parameter beta greater than 0, let's look at how Brownian paths bt grow as t goes off to infinity compared to the polynomial rate t to the beta. And here's the result. As with the local continuity properties, it all depends on where beta is relative to 1/2. If beta is greater than 1/2 here, if this thing in the denominator grows faster than the square root of t, then this ratio goes to 0 as t goes to infinity. On the other hand, if beta is less than 1/2, then this ratio goes to infinity as t goes to infinity. And all of those are almost sure statements. Almost every Brownian path has these properties. Notice that this is kind of reversed from the local Holder continuity properties. If beta is less than 1/2, then bt is beta holder continuous on any compact time interval, which would mean if that were globally true, you would expect this to be finite with beta less than a half and infinite otherwise. But in fact, in the large limit, it's reversed. And it's reversed precisely because, as we'll see, time reversal exchanges beta less than 1/2 with beta greater than 1/2. So here's how we're going to prove this. Instead of working with our original Brownian motion, we'll work with the time-inverted Brownian motion, CT, which we've already proved is a Brownian motion. Now that means, from what we proved in previous lectures, that this process, CT, restricted to the unit interval from 0 to t, is almost surely alpha holder continuous on that whole interval for any alpha less than 1/2. That is to say, there exists some constant, k alpha, which is actually a random variable, but is almost surely finite, as we know it's actually an LP random variable for some appropriate p, such that the increment cs minus c0, if we like, is less than or equal to k alpha times s minus 0 to the alpha for every s in the unit interval. But c0 is 0, and cs is just s times b 1 over s. If we now take t to be 1 over s, what that says is that 1 over t times bt is less than or equal to k alpha t to the minus alpha for all t bigger than or equal to 1, since s is less than or equal to 1. Now we can just bring this 1 over t over to the other side, and we get that bt is less than or equal to k alpha times t to the 1 minus alpha for all t bigger than or equal to 1. Now let's look at the case beta bigger than 1/2. If beta is bigger than 1/2, that means that it's bigger than 1/2 plus epsilon for some epsilon. That is, there exists epsilon greater than 0, such that even beta minus epsilon is greater than 1/2. And so what I'm going to do is define alpha, which for everything we've done over here could be anything less than 1/2. Alpha will be 1 minus beta minus epsilon, which is 1 minus something bigger than 1/2, which is therefore less than 1/2. And so from the calculations we've just done, it therefore follows that bt is almost surely less than or equal to k alpha times t to the 1 minus alpha, which is beta minus epsilon. Well, I'll just divide through by that t to the beta and get that bt over t to the beta is almost surely less than or equal to k alpha times t to the minus epsilon for all t greater than or equal to 1. And letting t go off to infinity here shows that this does indeed go to 0, verifying that first claim there. Great. Now, what about the case where beta is less than 1/2? Well, on the other hand, per what we proved in lecture 54.2, the lemma at the beginning of that lecture, the lim sup as s goes to 0 of a Brownian motion, which we'll realize in this case as the time-inverted Brownian motion cs, divided by s to the alpha, is infinite for any alpha bigger than 1/2. So we'll do the same sort of thing here. We'll choose alpha so that it's equal to 1 minus beta. That's fine here because we're interested in the case where beta is less than 1/2, and therefore this alpha will be bigger than 1/2. Now let's just set t equal to 1 over s, and that means that the lim sup as s goes to 0, that's the lim sup as t goes to infinity of c 1 over t to the minus alpha. Well, that's exactly this lim sup here, so that's equal to infinity. But that's the lim sup t going to infinity of t to the alpha times c1 over t. c1 over t, from our usual relationship, just reversing the role of t and 1 over t, is 1 over t times bt. But that's the lim sup t going to infinity of bt over t to the 1 minus alpha, which is exactly what we were interested in, the lim sup t going to infinity of bt over t to the beta. And that is equal to infinity almost surely by that lemma, which proves the other half of this claim. So the modulus of Brownian motion grows more slowly than t to the beta for any beta bigger than 1/2, but grows faster than t to the beta for every beta less than 1/2. Now we'd like to have a sharp result there. Maybe it grows exactly at rate 1/2, which seems consistent with the central limit theorem scaling. But it's important to note that the central limit theorem is a weak convergence result, which is even weaker than convergence in probability. Whereas here we're talking about almost sure convergence. It's certainly possible for a sequence to converge in probability, but not almost surely. And that's exactly what happens here. This brings us to the sharpest result possible about the growth of Brownian motion, which is the law of the irritated logarithm, as I like to call it. The exact rate of divergence of Brownian motion's modulus was computed by Khinchin and independently by Kolmogorov in the 1920s, with refinements later provided by Hartmann and Wintner and many others. And here is the statement. If I take Brownian motion, which I know if I rescale by t to the beta is either going to blow up or be 0, depending whether beta is bigger or less than 1/2. But what if it's really close to 1/2? Well, here's what the precise notion of really close means. If I divide bt by t to the 1/2 and an additional log factor, 2t log t under the square root, then the lim sup of that is neither 0 nor infinity, it is 1. And also the lim inf of that, which I can record by putting a minus sign here since minus bt is also Brownian motion, the lim inf of that is -1. So at this exact scaling, almost surely the Brownian motion stays exactly in between -1 and 1, oscillating infinitely often between the two. We are not going to prove this theorem. We will, over the last 2 weeks of the course coming up, prove some nice results that would allow us to then prove this theorem if we had another 2 weeks. The thing is, while this is a beautiful, sharp result, it is not as applicable as many of the other results that I'd like to save our remaining time to get to. So if you are interested in reading a proof, you can find one in Duret's book or in Kallenberg's book, but we will just content ourselves with the blunter law of large numbers that we proved on the last slide. I will say that it's also possible to deduce from this and arguments related to Donsker's central limit theorem that the exact same law of the iterated logarithm holds for random walks. That is, if we take xn iid L2 standardized random variables and take their progressive sum, then you have the exact same result. Sn over the square root of n log n exactly oscillates between root 2 and minus root 2 infinitely often. Let me just reiterate what I was saying on the last slide in this precise framework here. From the classical central limit theorem, we know that Sn over root n converges weakly to a standard normal, which makes it seem hard to understand how you can rescale by something that still blows up further times that square root of n and get something other than 0. Indeed, it follows from this that Sn over root n times something that blows up times the square root of 2 log n converges weakly to 0, and since it converges weakly to a constant, it in fact converges in probability to 0. So how can we have this convergence in probability to 0 here, but not here? Well, what that tells us exactly, referring to the definition of convergence in probability, is that if we take Sn over the square root of 2n log n, then that is very likely to be less than any fixed epsilon, with probability approaching 1 as n tends to infinity. That's for each fixed epsilon. But what we're seeing here from this law of the iterated logarithm is that at this exact scale, we get that this quantity here actually is still greater than epsilon infinitely often for any epsilon less than 1. Almost surely. So even though the probability of this event is getting smaller and smaller and smaller, it still keeps happening as n goes to infinity again and again and again and again. This is a fantastic demonstration of the fundamental difference between convergence and probability and almost sure convergence.